So let's start. So hi everybody, I am Neelav Bhatiya and I attempted my JEE in the year of 2020, wherein I secured an AIR of 1755. In the previous session, we had started the chapter sequence and series, and we had completed exercise 8.1, and we had also gone through some, at least half of the part of exercise 8.2 as well. So in today's session, we'll be seeing all the other questions that are remaining of this particular exercise, and we are going to find out how we're going to be able to solve them, right? So up until now, you might have been very familiar with all the formulas that are involved in the chapter sequence and series, and going further, the formulas are not going to be very different from what you have previously learned. That the questions are just going to be applications of these formulas, and yeah, so that is how we are going to proceed from here on out. So without wasting any more time, we can actually start with the remaining part of exercise 8.2 as well. So in exercise 8.2, we not 8.3, 8.2, we saw the first 16 odd questions. We had solved the last question that we solved in this exercise was find a GP for which the sum of first two terms is -4 and the fifth term is 4 times the third term. This was the last question that we solved. And moving further, we are going to solve the remaining ones, right? So without wasting any more time, question number 17. Right. So question number 17 asks of us if the 4th, 10th, and 16th term of the GPR X, Y, and Z respectively, prove that X, Y, Z are in a GP. Right. So let us first write what have been given. Right. So in the given section, we have X term, X, or the X is denoted by the 4th term of a GP, right? Let us say the GP that we're talking about is having the first term as A, and the common ratio of this particular GP is R, right? So how are you going to write the 4th term? The 4th term, any term of the GP is denoted by nth term is equal to A R raised to the power n minus 1, correct? So the 4th term of the GP is going to be A R raised to the power 4 minus 1, and that is going to be 3, right? So X is equal to A R cube, right? Similarly, Y has been told us that it is a 10th term of the GP. Going by the formula that we just understood, that the nth term of the GP is going to be equating to A R raised to the power n minus 1. The 10th term can be denoted by A R raised to the power 10 minus 1, and that is going to be 9, right? Similarly, Z has been said that Z is the 16th term of this GP, right? So again, plugging in the values of n in the formula that we have, we get Z as equating to A R raised to the power 15 minus 1, and that is going to be 14, right? So these are the three equations that I have been given, and from these three equations, I'm going to be proving that these three terms are also in a GP. Right? So to prove that these particular terms are in a GP, would it be sufficient for me to prove that Y upon X equal to Z upon Y? Would that be sufficient? Now ponder over it. If any three random terms are said to be in a GP, the common ratio that they have amongst them is always going to be the same, right? So if I divide the second term by the first term, it is going to be equal to the third term divided by the second term, right? Because the ratio between every consecutive term in a GP is going to be the same, correct? So if I prove that Z upon X equal to Z upon Y, Y upon X equal to Z upon Y, then that will be sufficient for me to prove that these three terms are in a GP, right? So here I'm going to solve LHS right here, and here I'm going to solve RHS, right? So what is LHS? LHS has been said to us as Y upon X. Y upon X is nothing but A R raised to the power 9 upon A R raised to the power 3, right? Seeing this, we can cancel a and a out. This gets cancelled, and the numerator gets reduced to r raised to the power 6. That is what we get when we divide y by x, we get r raised to the power 6. Similarly, on the RHS, we have z upon y. Z upon y, z has been said to us is a r raised to the power 14, and y has been given to us as a r raised to the power 9. Am I doing this correctly? Yeah. This wait, I might have goofed up some. Okay. Also, sorry. Z is not a raised to the power 14. It's actually a raised to the power 15, because we have been told that Z is the 16th term of the GP, not the 15th term, right? So I wrote that by mistake. So this is going to be 15, right? So you can cancel a and a out again, and when you cancel the numerator and denominator, what you're left with is r raised to the power 6. Now, as you can see, we have the LHS equal to RHS, and as the second term and the first term are in the same ratio as the third term and the second term, we can say that these three terms are in a GP. Correct. Moving on to question number 18. Question number 18. In question number 18, we have been asked to find the sum to n terms of the sequence 8, 88, 888 and 8888, right? So the sequence has been given to us along these lines. So the sequence is 8, we have 88, we have 888, we have 8888, and so on and so forth, right? Now I'm going to be solving this particular question by converting this sequence into a GP. Let's see how I'm going to do that, right? So let's denote this by S. So we have been given to us. So this is the sequence. This is the sequence that has been given to us. Let us denote that the sum of n terms of this particular sequence, Sn, is denoted by Sn, and that would then be something like this, right? N times. Right. So because R is going to be the nth term, right? The nth term is going to be 8 n times, right? So can I take out 8 common from all these terms, right? Let us see what happens when I do that. So can I write Sn as 8 taken out common? What I'm left with is 1 plus 11 plus 111, and going up till 11 n times, correct? This is nothing. I've just taken out 8 common from all these terms, and that happens because when I multiply 8 into the bracket, what I'm going to get is the sequence that I started with, right? 8 into 1 is 8, 8 into 11 is 88, 8 into 111 is 888, and so on and so forth, right? I've done nothing but I've taken 8 common. Now what I'm going to do is I'm going to multiply the numerator and the denominator by 9. So my Sn now becomes 8 into 9 upon 9, and into the bracket I have 1 plus 11 plus up till n times, correct? This is what I have in the numerator and denominator. And what I'm going to do now is I'm going to propagate the value 9 into the bracket. So I'll multiply 1 with 9, I'll then multiply 11 with 9, and so on and so forth. And when I do that, what I'm going to be left with is Sn equating to 8 upon 9. Now in the brackets, I have something like 9 plus 99 plus 999, and so on and so forth, right? The last term that I'm going to have is 9 n times, correct? That is what I'm going to have. Now when I've done that, can I write each and every term in this bracket as being 1 less than a power of 10, right? Let's see, I'm going to do that. So what I mean by expressing each of the term in bracket as 1 less than power of 10 is that me expressing the terms inside the bracket as something like 10 minus 1 plus 99 can be written as 10 square, which is 100 minus 1. 999 can be written as 10 cube minus 1, and n times 9 can be written as 10 raised to the power 9, 10 raised to the power n minus 1. Correct. I've done nothing. I've just subtracted uh, I subtracted 1 from each power of 10, and that is what I'm left with. If you now observe carefully, these terms 10, 10 squared, 10 cube up till 10 raised to the power n are going to form a GP, right? And in the end, you subtract 1 n times from all of these terms. So our Sn now becomes 8 raised to the power 8 upon 9 into 10 plus 10 square plus 10 cube up until 10 raised to the power n minus 1 minus 1 minus 1 for n times. Correct. Now, as you all know, that the sum of any GP is going to be a r raised to the power n minus 1 upon n upon r minus 1. Right. So in this particular GP, I have the first term as 10. The common ratio is also 10, and I have n terms. Right. So Sn now becomes 8 upon 9. I'm just going to convert the summation of the GP into the formula that I just told you. And now Sn would now become 10 into 10 raised to the power n minus 1 upon 10 minus 1. And in the on the other side, I will subtract 1 for n times. So this is what I'm left with. Correct. Simplifying this, what I'm now left with is I'm going to multiply 8 upon 9 in both the terms of the numerator and denominator. And what I'm going to get is 8 upon 9 into 10 upon 9, 10 raised to the power n minus 1 minus 8n upon 9. Multiplying into the first term again, what I'm left with is 80 upon 81, 10 raised to the power n minus 1 minus 8n minus 1. Correct. And that is going to be your solution for expressing the sum of n terms of this particular sequence. Right. Moving on. And we are going to now solve the 19th question. In the 19th question, we have been asked to find the sum of the products of the corresponding terms of the sequence 2, 4, 8, 16, 32 and 128, 32, 8, 2 and half. Right. So first, what has been asked of us? We have been asked to multiply each of the corresponding terms of the sequences, and then we have been asked to find out the summation of these terms up until half. Correct. How are you going to do this? We are just going to express the required sum, and we are going to take out the common 2's power out of it, and we're going to express this as a GP, right? So first of all, just let me just write down how the sum is going to look like, right? We have been asked to multiply corresponding terms. So the summation would then entail 2 into 128 plus 4 into 32 plus 8 into 8 plus 16 into 2 plus 32 into half. Right. This is what has been given to us as the sum. Right. From this summation, can I take out 64 as common? Can I do that? Let's see what happens when I do that. So I am going to take 64 as common. 2 into 128 is nothing but 256. And when you take out 64, when you divide 256 by 64, we are left with 4. Plus 4 into 32 is 128. When you take out 64 common from that, what you're left with is 4. Right? When you take out 64 common from 64, what you're left with is 1. Plus when you take out 64 common from 32, you're left with half. Plus when you take out 64 common from 16, what you're left with is 1 upon 4. Right? So this is what is left in the bracket. Now, this entire sequence is forming a GP of its own. So 4, 2, 1, half and 1/4 is a GP with A as 4. The first term is 4 and the common ratio as half. So the sum of this particular GP can be expressed as Sn of any GP, and that is going to give you the final answer, right? So the next step is going to be me writing the summation of this particular GP in the Sn formula, and that is how I'm going to arrive at the answer. So S is going to be 64. In the brackets, you now have the first term A. In the common ratio, you have 1 minus the common ratio is half. So that will be half raised to the power the number of terms in the sequence, and that is going to be 5. In the division, you have 1 minus, in the brackets, you would now have half, right? So that is going to be your sequence sum, right? You have as, let us express 64 as something, it's 2 raised to the power 6, right? So 64 can be written as 2 raised to the power 6. Into, you have 4. You can write that as 2 raised to the power 4. In the denominator, you have half. Half can be written as 2 raised to the power minus 1. And in the brackets, you have 1 minus 1 upon 2 raised to the power 5, and that is 1 upon 32. Correct? That is going to be your summation. Correct? The powers get added up. So here you have 2 raised to the power 9. And here you have 1 minus 1 upon 32. Correct? That is going to be nothing but 2 raised to the power 9, 31 upon 32. Correct? Now, 32 can now be written as 2 raised to the power 5. So what you would now have is 2 raised to the power 9 into 31 upon 2 raised to the power 5. The power gets cancelled. What is left with is 2 raised to the power 4. And we have 2 raised to the power 4 into 13, and that is nothing but 16 into 31. And we solve this, the final answer that you're going to get is 496. That is how you're going to arrive at the summation of this particular sequence, and that is how you do it quickly. Imagine if you had multiplied each of the terms separately and then added up, it would have taken a long time. Doing it this way is kind of faster and would help you to arrive at the answer more quickly, right? So moving on, let's see what the next question tells us. In the 20th question, we have to show that the products of the corresponding term of the sequence AR is AR square and up until AR raised to the power n minus 1 and capital A, capital AR square up until capital A, capital R raised to the power n minus 1 form a GP, and we also need to find the common ratio, right? So I'm just going to do that by proving that the ratio between each of the consecutive term in this GP, when you multiply the corresponding terms of these two GPs, is going to be the same, right? So I'm currently solving question number 20. The first GP, GP1, is A, then you have AR, then you have AR square, so on and so forth, up until AR is to the power n minus 1. This is GP1, right? GP2 is going to be AR square up until AR is to the power n minus 1. So the sequence that is obtained by multiplying the corresponding terms of these two GPs is going to be something like AA plus right? Plus and lastly you would have, sorry, there's no plus sign right here, once, and the last term would be AA r raised to the power n minus 1, capital R raised to the power n minus 1. So, to show that this particular sequence, that is multiplication of the corresponding terms of these two GPs, is going to be a GP in itself, it will be sufficient to show that the ratio between the second term and the first term is going to equate to the third term and the second term, right? So, if I show that second term divided by first term is equal to third term divided by second term, that will be a sufficient condition for me to prove that this is going to be my GP, right? So the second term is this, right? And the first term is A. A gets cancelled. So on the LHS, you have RR, and third term divided by second term is going to be A r square r square, and the second term is a r r, right? A and A gets cancelled, this gets cancelled one time, and similarly on the RHS also you have r. So small r capital R, small r capital R is equating in both the LHS and RHS, and that is going to be your common ratio. So the common ratio of the newly formed GP is going to be r, and the first term of this GP is going to be the first term we obtain, and that is small a capital P. Correct. And that was the solution. That is how we showed that these terms are in a GP. And yeah. So moving on to the next question. Question number 21, we have been told that find four numbers forming a geometric progression in which the third term is greater than the first term by 9 and the second term is greater than the fourth term by 18. Right? So, we have been told to find a geometric progression which has four numbers. Let us assume these particular numbers to be AR square, and AR cube. So this is your first, second, third, and fourth term respectively, right? Let us form the equation that have been given to us in the question. We have been said that in which the third term is greater than the first term by 9, right? So T3 is equal to T1 plus 9. And the second equation that has been given to us is that, and the second term is greater than the fourth term by 18. Correct. Now substituting the values of these equations into of these values into the equations, you have T3, and that can be written as AR square equal to AR plus 9, and here you have AR equal to AR raised to the power 3 plus, I'm sorry, this is just going to be AR raised to the power 3 plus 18, right? Let us take this common here. So A r square minus 1 is going to be 9, and here I will take minus a common, so I'll get minus a r square minus 1 equal to 18, right? And I will have to take AR common here. So minus AR I have taken common in the second equation. The first equation I have taken a common, right? Now let us denote this by third equation and this by fourth equation. When you divide the third equation by fourth equation, what you get is minus AR, r square minus 1 equals to 18 upon AR, just A, r square minus 1 equal to 18 upon 9. This gets cancelled two times. This entire thing gets cancelled, and this gets cancelled. R is equal to minus 2, and substituting the values of r equals to minus 2 in the first equation, we'll be able to solve for a, right? So the equation is ar square is equal to a plus 9. Plugging the values of r equals to minus 2 here, you have 4a equals to a plus 9, 3a equals to 9, a equals to 9 by 3, that is going to be 3. So all in all, the equation, the four terms of the GP that you're going to get is 4, minus 6, 12, and minus 24, right? These are the four terms of the GP. Moving on, question number 22. If the pH, QH, and RH term of the GP are A, B, and C, prove that A, Q raised to the Q minus R into B, R minus P into C, capital into C, P minus Q are going to be the same, right? Are going to be equal to 1, right? So this has been said to us that we need to first assume the P, R, Q, and R term of the GP as A, B, and C, and then we need to prove that these particular terms raised to the power Q minus R and so on and so forth are going to equate to 1, right? So this is nothing. I've just substituted the values of PQ, I mean ABC and PQR in the LHS of the proof that, and that is how I'm going to arrive at the RHS, right? So the P8 term has been given to us as A. So let us assume this particular GP to be A, or for the sake of it, let's assume it's going to be A, capital A, and the common ratio is going to be capital R, right? So the P8 term of this GP is which is A. P8 term equal to A, R raised to the power P minus 1, and that is going to be A, right? The QET term is going to be A, R raised to the power Q minus 1, and that is going to be B. And R term is going to be A, R raised to the power R minus 1, and that is going to be C, right? And prove that we have A raised to the power Q minus R, B raised to the power R minus P, and C raised to the power P minus Q is equal to 1. So the LHS would then be A, substituting the values of A from above, we have A, R raised to the power P minus 1 raised to the power Q minus R into B, you have B as A, R raised to the power small q, Q raised to the power minus 1 into power into, we have R minus P, right, raised to the power R minus P, into, you have C, that is A, R raised to the power R minus 1 raised to the power P minus Q, right? So whenever you do that, the powers are going to get multiplied, right? So A's power right here is 1. 1 multiplied by Q minus R is Q minus R. So the first term is going to be A raised to the power Q minus R into R raised to the power. So P minus 1 into Q minus R, that is going to be PQ minus Q plus R, correct? Similarly, for the second term, you're going to get A raised to the power R minus P, capital R raised to the power RP minus PQ RP minus PQ minus minus r plus p. Correct. For the third and the final term, it's going to be a raised to the power p minus q r raised to the power pr. Sorry, it's going to be pr. Is it going to be pr? I don't think so. It's not going to be pr. I'm sorry. So here I wrote this term as false. It's going to be rq. It's going to be pr. It's going to be pr right here minus e plus r plus q. Right. That is how this particular term, or wait, I something wrong right here as well. You multiply this carefully. So you have PR minus RQ. You also have minus P, and you have plus Q, right? So we have all these terms in the power. We can now, and all these terms are in multiplication as well, you can just add all these powers up and let's see what we get then. And minus R. So all these terms are going to get cancelled out, and what you're left with is a raised to the power 0, r raised to the power 0, and that is going to give you 1. That was nothing but the RHS that you begin with, and so we have proved that the equation that was given to us was true, right? It was a very lengthy question. It had many complications, many intricacies involved. I would urge you all to try this on a pen and paper, and that is how you're going to arrive at the answer faster, right? So once you've done that, you're going to write exercise 8.2 again, and we have solved question number 22. Let us see what question number 23 asks of us. Like question number 23, we have, if the first and the nth term of the GP are a and b, and p is the product of n terms, prove that p square equal to ab raised to power n. Right. So we have been said that a and b are the first and the nth term of the GP. Let's assume the GP to be a, having the first term as a, the common ratios are. So a would be a raised to the power a, and b, which is the nth term of the GP, is going to be a raised to the power n, r raised to the power a into r raised to the power n minus 1. Now, if p is the product of n terms, so the product of n terms, what is that going to be? The product of n terms is going to be a into a r into a r squared and up until a r raised to the power n minus 1, right? That is, when you add all these powers up, you get a raised to the power n, because it has been added up n times, and you get r 1 plus 2 plus 3 up until n minus 1. This right here is a AP, and when you add up the first n natural numbers of an AP, what you get is, when you add up an AP with first term as 1, number of term as n minus 1, and common ratio as d, you are going to substitute the values of n summation of an AP, and that is nothing but n upon 2 into the bracket 2a plus n minus 1 into d, and that is what I'm going to do here. So r would become n minus 1. Why have I written n minus 1? I have written this because the number of terms in the GP are n minus 1, in an AP are n minus 1, divided by 2, 2a, 2 times the first term, that is nothing but 2 in itself, plus n minus 1, and the common ratio has been, or n minus 1 minus 1, and the common ratio has been given to us as 1, right? When you solve this, you get a raised to the power n. When you open up these brackets, what you get is r n minus 1 divided by 2, 2 plus n minus 2. So 2 and 2 gets cancelled, and what you're left with is a r raised to the power n into r a raised to the power into r raised to the power n into n minus 1 divided by, right? So that is something that is given to us. So that is a solution for p. When you square this up, so this is p, the product of p terms. In the LHS, we have been given p square. So LHS, you have p square, and we square this up, you get a r n into n minus 1. Correct? So this is your LHS. Now for RHS, you have a into b raised to the power n. So RHS, you have a, which is a, the first term of the GP. B has been given to us as the nth term of the GP, and that is going to be a r raised to the power n minus 1. This entire multiplication has been raised to the power n. Then you do that, you get a squared into r raised to the power n minus 1 whole raised to the power n. Powers get multiplied. What you are finally left with is a square r raised to the power n minus 1 into n, and this is equal to your LHS. That is hence proved. Correct. Moving on, in question number 24, we have to show that the ratio of the sum of the first n terms of the GP to the ratio from n plus 1 to 2n term is r raised to the power 1 upon r raised to the power n. Right. So let us assume the GP to have, so in question number 24, let us assume the GP to have the first term as a common ratio as r. Therefore, the sum of the first n term of this particular GP is going to be Sn is going to be a r raised to the power n minus 1 upon r minus 1. Correct. So that is going to be your Sn term. What is going to be the n plus 1 term of this GP? N plus 1 term is going to be a r raised to the power n minus r raised to the power n, and the 2n term of this particular GP would be a r raised to the power 2n minus 1 terms, right? So these are n other terms with common ratio as r, and the first term as a raised to the power rn, right? So Sn first, and now we're going to find out Sn second when the GP now begins from the nth term of the previous GP, which was which is going to be a into r raised to the power n. The second GP is going to be having the first term as a raised to the power n minus 1. The number of terms is n again. So we in the bracket we have r raised to the power n minus 1. Common ratio is r again. So in the denominator you have r minus 1. So we have been asked that Sn1 upon Sn2, we need to prove that this is going to be 1 upon r raised to the power n. So let's just divide the first summation by the second summation. So in the LHS, you would now have a r n minus 1 upon r minus 1. When you divide it by the second series, it becomes the reciprocal and gets into multiplication. So in the multiplication, you would have r minus 1, and here you would have r raised to the power n minus 1, right? So because this is the first term of the second GP, and because it has n terms, so this term is right here, and this is the this is here because the common ratio is going to be the same, right? So this gets cancelled, this gets cancelled, a and a gets cancelled, and what you're finally left with is 1 upon r raised to the power n, and that is going to be your RHS as well, right? So hence proved, right? Moving on, question number 25, right? If A, B, C, and D are in a GP show that a square plus b square plus c square into b square plus c square plus d square is equal to AB plus BC plus CD, the whole square, right? So this is going to be an interesting question because this is going to involve a lot of calculation on our part, but we'll try our best to be done with this, and let's see how that goes, right? So firstly, we need to say what the first four terms of this GP are going to be, right? Let's assume the GP to have the first term as capital A and to have the common ratio as capital R. So A, which is going to be let's assume A is going to be we have A, B, C, and D, which are said to be in this GP. Let's assume A to denote the first term of the GP. So A is equal to A, B to denote the second term. So B would be AR, C would be AR square. Subsequently, D would be AR cube. When you do that, the LHS would be A square plus B square plus C square into B square plus C square plus D square. Plugging the values of A, B, C, and D from the above equation, you get A square as capital A square, B square as capital A square, R square, plus C square as capital A square, R raised to the power 4, right? And in the second term, you have B square, that is again going to be A square, R square. C square is going to be A square, R raised to the power 4 plus AR cube, and AR cube is going to be nothing but A square R raised to the power 6, right? Doing this, what you are now left with is you can take out certain terms common from each of these terms, and let's see what you get when you do that, right? So you can take out A square common from the first equation, right? So when you do that, you get A square, and here you get 1 plus R square plus R raised to the power 4. From the second term, you can take out A square R square common. When you do that, you get A square R square. In the bracket, you get 1 plus R square plus R raised to the power 4. When you simplify this, you get A raised to the power 4 R square into 1 plus R square plus R raised to the power 4 whole square. And this is going to be your LHS, right? Similarly, when you solve it for RHS, you have the RHS is going to be AB plus BC plus CD whole square, right? What is A into B? A into B is A into AR plus what is B into C? B into C would be nothing but AR into AR square plus CD would be nothing but AR square into AR raised to the power 3. What I've done is I've just plugged in the values of A, B, C, and D into the RHS part, and I've just squared this entire term because that is what RHS is going to be. Let us take out A and AR common from, or let's take out A square R common from all these terms, right? When you take out A square R common from the first term, you get A square R, and this is going to be squared, mind you, because we are taking out the square common. So you get just 1 here. When you take out A square R from common from this term, you're going to get R raised to the power 2 remaining. And when you take out A raised to the power A square R common from the third term, you get R raised to the power 4 remaining. That is going to be whole squared, right? So A square R the whole squared is going to be A raised to the power 4 R square, and in the bracket you would now have 1 plus R square plus R raised to the power 4 common, the whole square, right? This is this is nothing but equal to LHS. As you can see right here, the LHS that we found was this, and yeah, the RHS is going to equate to same. So you can say that LHS equal to RHS, hence proved. Correct. That was the 25th question, I believe. We have done questions from 16 to 25. The coming lectures, we are going to discuss the remaining questions from this exercise. And yeah, we are also going to potentially see and try, if you have some time, we are going to try the remaining exercise as well. Right. So this was 25th question in exercise 8.2. And yeah, that was all. Thank you.